Hey guys, welcome to the IICPC summer camp. So, just a brief introduction on what the IICPC summer camp is, if you don't already know, and then we'll be starting with today's session on graph algorithms by the one and only Mohit Agrawal. Right? So, what is the IICPC summer camp, right? IICPC stands for Inter IIT Competitive Programming Conclave, and our goal for this summer was to give out the best competitive programming content that is there to offer. We wanted to build a community and we are trying our best to do that. Now, this camp is free for all, but it wouldn't have been possible to make this free if not for our sponsors. So, who is sponsoring our camp, guys? First of all, it is AlgoZenith. So, what is AlgoZenith? It is a premier platform for internship and placement preparation. So, if you are planning to land an intern somewhere or placement, it's a really great website. Apart from that, they have comprehensive courses on DSA, web development, CS fundamentals, and whatnot. And the thing is, the people who have cracked good companies from this institution, they are not only from IITs, but also from tier 3 institutions. So you can consider logging in to AlgoZenith today for premier content on internship and placement preparation. Apart from this, they are also providing us a platform for hosting this IICPC camp. So the novice and advanced camp are there. We'll show you in some time. Thanks a lot for AlgoZenith for sponsoring this camp. Apart from that, the 0x PPL. So the interesting thing about 0x PPL is that it was founded by Prasanna Sankar, who previously founded Rippling. Rippling is currently a $10 billion plus company. But the interesting thing is this team is full of competitive programmers, right? Prasanna Sankar himself during his time was #1 on Top Coder, ACM ICPC, and Google CodeJam, all when he was age 18. So a good thing is you can get good at competitive programming through this camp and then apply to 0x PPL and spread impact throughout the community. Thanks a lot for 0x PPL for sponsoring this camp. Now, it's going to be on minimum spanning tree and it is going to be hosted by Mohit Agrawal. Mohit Agrawal is All India rank 15 on Codeforces right now and he's a really great educator. So I hope you guys enjoy today's session. Let's get started with the session.
Okay. Hello everyone. Thank you for the introduction, Gaurish. So I am Mohit Agrawal, and today I'll be a mentor for disjoint set union and minimum spanning tree. So without further ado, let's get started. So how this session is organized is first I'll go over the motivation of DSU, what that means, what you can do with the DSU. Then we'll go over introduction to DSU. We will see how to implement DSU. Then we will see how we can optimize DSU. Like in there, we will study path compression and union by rank or size. And then we will see applications of DSU, that is like finding cycles in the graph, finding connected components, finding minimum spanning tree. That is nothing but Kruskal's algorithm. Okay. So, what is DSU basically? So, DSU is basically a data structure that can be used to represent disjoint sets. So, what is disjoint sets basically? Basically, disjoint sets means you have collections of sets in which, if you take intersection of two sets, it is basically a null set or union set. So uh, let's see, if you have two sets A and B, let's say these A and B are two sets, and A and B are disjoint sets if and only if the intersection of A and B is equals to phi. Phi is null set. So that is disjoint sets. So DSUs DSUs is nothing but a data structure that allow you to handle this type of things, like disjoint sets. Now, let's see what can you do with DSUs. So first of all, let's consider you have two disjoint sets, X and Y. Let's say you have two disjoint sets, X and Y. Now, what are the operations in it? What can you do with it? The first operations of DSU is find set. So what find set does is, like, if you call this function on the DSU, like let's say find set of one, each find set of one, it should give you X because one is present inside X. Now find set, yeah. Now when you call find set on 11, it will give you Y. But this is not exactly true. This is not exactly true. It doesn't, like, you don't represent sets in computer using like letters, because they can be like a millions of sets you are handling with, and you cannot assign alphabet to each other. So what we instead do is represent each disjoint set with an element of that set, meaning we pick one element from this set, like from 1 to 5 9. Let's say we pick 2 and call it a leader or a root. So let's say you have two sets, 1 9 15 and 2 7 5. What we do, instead of assigning letters to these sets, we assign a number, which is basically an element of the set belonging to that set. So for 195, let's say its leader is 1, and 2711, let's say its leader is 2. So find set will give you the root instead of the letter. Yeah, see, that's what we have written in the slide. It finds the set where n belongs to. We represent the set using an element of that set called the root of that set. It is also called leader. So find set of 1 will give you 1, and find set of 7 will give you 2, and so on and so forth. The another very powerful operation of DSU is union operation. So consider you have two disjoint sets, right? Uh, let's say you have two disjoint sets, this one and this one, 1 4 7 9 and 2 and 6. DSU provides a method to take union of these sets. So after you call union of 1 comma 6, the, like, union on the roots, like why 1 comma 6, because 1 represent this set and 6 represent this set. When you call union on of these two sets, you will the DSU data structure will contain only a single set, 1 4 7 9 2 and 6, and the root of this set will become 1. Yeah. Now what will happen if you call union of 1 comma 4? Since both the elements occurs in the same set, the union operation will not do anything at all. Yeah. And like if you call union of 7 6, it will like give you the same result. Like this will happen even if you call union of 4 6. Like if you call union on elements which are belonging to different sets, it will basically merge it. And if the both elements occurs in the same set, it will not do anything. So as a black box kind of thing, DSU supports two important operations. One is find set, which will give you the leader of a set given one element of that set, and the second operation is union operation, which will merge two sets given two elements of two different sets. Okay. Now, moving forward, how do you represent a DSU, right? Like representation of DSU is very important. So what we do here is for representing a DSU like structure, uh, Let's move to escalator first. For representing a DSU, we represent the DSU in a tree-like manner. Like let's say you have a set 1, 3, 6, and one more set 2, 5. These both disjoint sets are stored in a single disjoint set union. How will they be represented in the computer for efficiently doing both the operations? What are the both the operations of DSU? First, finding the root or leader, and second operation is merging two different sets, given elements of them. So you represent DSU in a tree-like structure. So in this case, you can like represent this as this. Parent of 3 is 1, and parent of 6 is also 1, but 1 is a root. What we do is there are two types of things people do. If there is a root, what people like to do is set its parent to -1, meaning there is no parent of this. Or what is most common is people set the parent of 1 to 1, meaning they create some self loop like this. And in this case, let's say 2 is the leader. In this case, people do something like this, and like this is how we represent DSUs in computer. And a single connected component is one set. So this is this is one set, which this is one set, and this is the second set. Also, to they will be a self loop for 2 also. Uh, so for representing DSU in computer, what we do here is we create an array. We call this array a parent array. For in this case, we have 6 elements: 1, 2, meaning 1 to 6, 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, and 6. So since we are representing the DSU in tree-like structure, we basically store the parent of every single node. So if we look at this first set, the parent of 1 is 1, parent of 2 we don't have no yeah we have node 2, so parent of 2 is 2, parent of 3 is 1, parent of 4 we don't have node 4, so let's not count it. Parent of 5 is 2, and parent of 6 is 1, right? Now, like can you identify which of the following nodes will be the root node? How can you like identify which of the nodes are root node using just the parent array? So if you look at the root nodes here, what are the root nodes here? We have two root nodes, 1 and 2, and hence there are two disjoint sets represented by this DSU. So how do you identify the root node? Like if you look at the parent array, if there is a self loop like parent of u equals to u, for some node u, like then we can like easily say that this like implies that u is a root node, right? So do you have now? How do we like? We know that DSU supports two types of operations. One is find set. So how do you implement a find set operation when you are given just a parent array? Like, what is the most simplest way to implement this? Like, let's go back to the slides. Like here, we see that we are representing DSUs like this, like this. They are initially four distance design sets. Uh, you can consider that they are like you can consider that these are like four sets, and like uh, although like they are not drawn or self loops, like you can consider them. Okay, so here we have like 1 2 3 4, like there are four design sets. Here we have 1 2 3 and 4, and 1 2 and 3 4, like this. We like represent the DSUs in some form of tree structure, like I have taught in the Excalibur. Now, what are the terminologies? First is the root, like I have explained you. Root is the representative of a disjoint set. Two nodes having same root is said to be in the same set. So let's say you want to check whether or not two nodes. Let's say whether you want to check two nodes, U and V, are in the same set or not. How do you check this? So you can check this like this. If you look at the tree structure, uh, if two nodes are in the same set, their root has to be the same, like from the tree. So we can say that if uh, if find of u equals to find of v. So find function will give you the root of u, and find u and find v. If both of these are equal, this means that u and v are in the same set. So that's what I have written here. Like in this diagram, 1 2 3 4 5 6 and 7, we have four different disjoint sets stored in a single DSU, and the roots of these are 2, 5, 6, and 7. That's how I have already explained how we identify the root. Now, uh, I've also explained how to write the parent array. Like for this example, uh, like the parent here is very similar to the parent in trees. Uh, like in this case, parent of one is two, parent of one is two, parent of two is two itself, parent of three is two, parent of four is five, and so on and so forth. The rest are self-explanatory. Uh, now we have talked about how do we find set. Uh, Now, how do we merge two different sets in DSU? So, how to merge these? Let's say 1, 2, 3, and 4. Let's say you want to merge 1 and 2. What we can do here is that, uh, let's say we have uh, initially this. Let's say we want to merge 1 and 2. How do we do that? What we can do here is that uh, we can we can cut this edge and set this like this. This is one way, or we can do the either way also, like cut the edge of this and merge this like this. Second method would be like cut this and merge this. So we can have two different type of DSUs. One is like this, and this, and the other would be in which 2 becomes the root and 3 and 4 stays the same. So if you want to merge two different uh, disjoint sets, you set the parent of their root to to the root of the another DSU. Right. Hope this makes some sense. Like now the sets represented by this DSU is nothing but 1, 2, 3, and 4. Right. You can go further here. Like you can go further here and merge like 3 and 4 and set the parent of 4 to 3, and like this will become 1, 2, and 3, 4. That's what I've explained in the DSU. Like you merge 1 and 2 and you get this DSU, and you set the parent of 2 equals to 1. Right. Now here for merging 3 and 4, what you do here is set parent of 4 equals to 3. So our DSU will become like this. Now if you want to merge both of these sets, now here it is interesting. We can do like we find the root of both of these sets. So uh, in this case the root here is this. We will just do this. We will just do this and get this one. Right. Now let's talk about the actual code implementation. First of all, we will see the naive implementation of DSU. So how do you implement the first operation, like find set of n? So there is one method, like we can do it iteratively, and the other method is we can do it recursively. So I've given you the recursive code. I'll tell you why, because it is very easy to implement optimizations in this. So let me explain you how do we find the root of disjoint set union. So let's imagine we have DSU like this: 1, 2, 3, and 4. So if you want to find the root of 4, how will you find this? What we do here is we start at 4. We start at 4 and we look at its parent. We look at the parent of 4. Now, since parent of 4 is not equals to 4, what does it means? That 4 is not the root of this DSU. So we will go to 3. What is 3? 3 is the parent of 4. So we move to the parent of 4 and then try to find the root of 3, because like root of, because both 3 and 4 exist in the same DSU, the same disjoint set. Therefore the root of 3 and 4 must be the same. So we go up, then we go up, then we go up until we find out 1, and 1 is the root because the parent of 1 is 1 itself. So that's how we find out that the root of 4 is equals to 1. 3 root of 3 is also equals to 1, and root of 2 is also equals to 1. That's how we find out the uh, that's how we find out the root. How do we how do you code it? One is the iterative implementation. You can maintain let me let me give you a rough idea how do you do that. You will let's say I'll give you a pseudocode. Let's say you want to find the root of u. How do you do that? You first of all check if parent of u, let's say you declare a pointer while parent of u is not equals to u, meaning u is not the root. We'll just go to parent of u, and then since after exiting from this while loop, u will be equal to parent of u, meaning there is a self loop, meaning you can just return u. We have reached to the topmost. That's how we you implement it recursively. Iteratively, you implement it like this. Key, you have a find set function. It takes in a parameter n for which you want to find the root of, and if parent of n equals to n, that means we are already at the root and we just return n. Otherwise, we return the root of parent. Find set, like we go one step above the that, right, right. So what will be its time complexity? So if we are building if we are building the DSUs naively, like we can have pretty skewed DSUs. Let's say we have created a DSU like this. We can have pretty skewed DSUs, right? One, two, three, four, dot dot dot, like this. So in the worst case, if you look at the worst case of this pretty skewed DSU, like you have to go n steps up. So so the time complexity will go of n, and the space complexity, we are not using any extra space, but we are using like O of n space to represent the DSU. So like the time complexity of this find operation is O of n, right? And we will see how we can optimize this. We will like go from n to O of n log n of log n. Like we will optimize this, and we will also further optimize. We will optimize it even further to go to like inverse Ackermann function. Like, and like it is basically, you can call it a constant function. Yeah, it is like, you can call it that. Like it is a very slow growing function. We will talk about it later. Let's see. So yeah, time complexity is of n. Now how do you union two different sets, two different design sets? So let's say you have a DSU like this. Okay, we are using the tree representation like this, and then you have another DSU like this. Okay, if you want to merge these two DSUs, how do you do that? I'm sorry, I'll use the term merge and union interchangeably. Like they basically mean the same thing here. Don't get confused. Merge and union are basically the same thing. How do you union these two different sets? Like I have like told you earlier that what we can do is we can cut this edge and just set this edge to here. So it is a pretty fast process. Like you just need to change a single edge here. um, so the only problem being like you have to find the root of it. So that's why it will suit up. So how do you how do you code it? If you look at the code, like it is very simple. You let's say you want to union two sets A and B. What we do here is we find the root of A. Like find set function will return the root of A, and then we do the same thing for B. we figure out the root of b, and if a and b are not equal, like we can probably remove this condition also, like it does not matter. But if a and b are equal, then we can say that both node a and node b are in the same set, so like there is no need to merge. Then yeah, if they are not equal, then only we like set the parent of b to a. What this operation will do is like it will do the same thing I explained here, that let's say this is b, let's say this node was b and this node was a, this node was b and this node was a. We just cut this parent edge and we drew a new parent edge from b to a, right? And we return the a, right? Let's move forward. Time complexity, like the time complexity of this function will, like we are using the find set operation. This is a constant time operation, but these two operations, like these two find set operations are a linear time operation, like as we have as our in our naive implementation in this one. So this union sets or operation will also be linear time. So that's why I've written here that the space complexity of this naive implementation of DSU will be of n, because we are still maintaining a parent array. Yeah. And the time complexity for finding set will be of n, because the trees can be skewed. For unioning the two sets, we are still finding the leader of the sets, so the time complexity will still be linear. Okay. Now, how do you optimize it? Because like linear is not a very good time complexity. Let's say we want to apply. Let's say n is around 1e5, and you want to apply like a million operations on DSUs. So that will easily like TLE. So we want to somehow optimize it. How do you optimize it? So there are two methods basically to optimize it. Uh, one is path compression, and one is union by size and rank. So what we do in path compression, let's see. In path compression, we does not change the merge implementation. Merge will still stay the same. What we do here is we will like compress the path from 1 to n. Let's say how path compression works. Let me explain. Let's say we still have a very pretty skewed DSU. Like because the merge operation is still the same. Like let me show you very simple. Let's say we have some disjoint sets 1, 2, 3, 4, 5, 6, like this, and you called merge operations a bunch of times, 5 times basically. First time you merged 1 and 2, and it became this. Then you merged 2 and 3, then it became this. Then you merged 3 and 4, then it became this. uh, then you merge 4 and 5, then it became this. And after that you merge 5 and 6, and it became this, like this. Let's say we merged nodes like this, and the DSU became pretty skewed like this. What path compression allows us to do, let's say we called, like after we created this DSU, we called find set of 6. What will happen? So what path compression says that if we find out this find set of 6, which comes out to be 1, right? We we will like delete this row, like when we like path find set, when we call find set, it not only like returns the root, it will also like reorder some of the edges. We will delete the edge from 5 to 6, like this. we will delete the edge from 5 to 6 and draw a new edge from 6 to its root, that is 6 to 1, like this. So remember our recursive implementation of find set. Let me show you. Yeah, this one. Remember our recursive implementation. In this recursive implementation, we like figure out the root of the n. Now, in this find set operation, we also like set the parent of n equal, which is equals to the root of this node n, right? So there is like just a very small change in code, but it's very important to understand how it works. So like this, like the parent of 6 will become a 1. Now when we call the find set of 6, it would also have called find set of 5. So in this case also, we remove this edge and create a new edge going from 5 to its root. So it would be like this. Now you may ask, like, Mohit, like, what's the big idea? Like, calling the find set 6 in the skewed DSU will still take linear time. What we have achieved here. So the thing is, uh, like the first find set operation, yes, you are right that it will still take linear time, but if we average out all the operations, like after the first, like let's say what will become of DSU after the first find set, which is really interesting. It will become like this. Instead of like this pretty skewed DSU, you will get a star like structure like this. Now the subsequent find set operation will be like really fast, because like let's say you after you call find set 6, now you call find set of 3. What would happen? Like find set of 3 will check whether or not 3 is root, which fails, and then it will go to 1 and it will return 1. So it will like take at most like 2 or 3 comparisons. So after the first find set, which may take around a linear time, the rest of the find set going further is like really fast, really fast. So I'll not go into the nitty gritty details of the time complexity proof, because I don't know myself also. So the time complexity of this find set operation, like the average time complexity, not the worst case, the average, you can also call it amortized. Average time complexity would be of log n per operation after applying the path compression, and the space complexity will still remain the same. And yeah, now let's say we use just the path compression optimization. The the find set operation optimized to overflog n. Now remember that our union operation also dependent on the find set operation, and our union operation also dependent on the find set operation. So the our union operation will also get optimized to of log n. So that this is the time complexity we get after just applying the find set operation, like from n to log n, like which is a really big improvement, uh, just by applying a very simple change here. Now what else you can do? Yeah. So in code, how do we do path compression? So in code, we will like just call in find set. Like the all of the lines are very same. We just set the parent of n to the root of that node, root of n. And what is the root of n? We will get this by recursively calling the find set function again, right? And like This is like very easy to implement. Okay, moving forward, union by size. So, like, let's see. You have consider you have two different DSs again. Let's say we have bunch of DS, bunch of sets. Uh, let's say we want to merge one and two. Like both of them have the same size, so it does not matter where we merge. So we let's say we merge it like this: one and three, four, five, and six. Right. Now we want to merge these two sets. So there are two things we can do. We can set the parent of 1 to 3, or we can set the parent of 3 to 1. That's the two things we can do when we are merging. So it depends on the the argument order also. Like in the naive implementation of union A comma B, it basically depends on the order in which the elements are passed in it. Whether 1 will be merged to 3 or 3 will be merged to 1. So what do you think is like a better way to do it? Like let's see both of the DSUs that will form here. The first DSU will be like this. First DSU would be like this: 3, 1, and 2. And the second DSU would be 1, 2, and we merged 3 to this DSU like this. Now this is the second DSU. Now in the first DSU, as you can see that like the height is 2. Now more height in DSU is bad because the find set operation will again have to go a bunch of nodes up. So but why we are applying why we are applying this optimization just achieve one purpose, like it does not let the height of the DSU grow too much. So when we have merged uh, 1 to 3 like this one, in this case the height grows a little larger, and but in this case the height does not increase too much, like it stays the same. Like previously also the height was 2, now also the height is 2. So as you can see here that yeah, the height does not increase much, or like just increase by a small margin. Like height can get at most plus 1 when you are merging smaller set into the larger set. When you are merging smaller set into the larger set. And when you are merging our opposite, like large to small, so in this case height does not increase by much. It sometimes increase by 1, but like it mostly does not increase. So like if height is not increasing, which is a good thing, like it is a very good thing, because the sole purpose of this optimization is like achieving the minimum height possible in the DSU. So right. So that's what like union by size means. Like it says that when merging two sets, the smaller set is always merged to the larger set. Using this strategy, we can avoid building a DSU with large height in the first place. Okay. So how will we implement it? So there is another feature we need to store, that is like the size of the DSU. Uh, so how do we like maintain it? Like I'll show you the full implementation later. Let's just see union by size implementation. We have to maintain and another parameter int size also, which basically has the size of the nodes. Okay. Now the another thing is like when we are merging, like you can see that the most of the code is like very similar to the naive implementation also. When we are merging two sets a and b, a is equals to find set of a and b is equals to find set of b. If a equals to b, we return like just as we did in the naive implementation. The only change you can see here is this line. Like this line is very important. If size of a is greater than size of b, we swap a and b. What this line ensure is that the size of a will always be smaller than size of b after like this if statement has been executed. Like this statement make the size of a smaller and b larger if it is not already that, right? So we are like merging smaller set into the larger set. That's why like a here is the smaller set and b here is the larger set. What we do here is we set the parent of a to b. What this does, it creates a link from a to b. And also what happens is that the size of b, like now the b set has like a higher set, like the larger set size. Now it is increased by size of a. Okay. Let me make something clear first. What is this like size thing? Size of u. Like in my implementation, this only makes sense if u is a root, like this. This this only makes sense if u is a root and it gives the number of nodes in a particular disjoint set, right? So that's what this size variable is, and we can easily maintain this when we are like merging two sets, when we are doing a union operation, right? So like if you are not applying, let's say you are not doing path compression, you are only using the union by size, then also the time complexity would be like we have not used the path compression, we have just used the union by size. In that case also the time complexity would be of log n for both the operation. Why log n? Because that the height, because the height of dsu in any moment will not increase more than log n. Like it is the maximum value of the height. Now like both of the optimizations are good enough on themselves also, on itself also. Like the path compression achieves log and time complexity by itself only without using union by size, and union by size also gets to that same time complexity. What if we like use both of the optimization, like the path compression optimization we use on find set, and union by size we only use in the union operation. What if we use both of the optimizations? Then like right, that the same thing I have written here. If we just use, if we use just one optimization trick, path compression or union by size, then the average time complexity will become O of log n. If both are used, then the time complexity will becomes O of alpha of n. What is alpha? Alpha is inverse Ackermann function. And if we like Google it or something, like alpha is very slow growing function. Uh, you know that. Let me tell you. Uh, this is like O of n. This is log of n, and like alpha is like really this line, like it does not increase at all. This is like log of n, like this is very rough graph to give you an idea. And like this is n square, like this. So the alpha is like very slow growing function. You can like people even treat it as like a constant function. You can like just if alpha is like too much, uh, you can even treat it like as a constant function. Like it is nearly as fast as a constant function. Like to give you some idea that O of uh, alpha of 2 raised to the power 64, that's the largest number you can store in long. It's like roughly equals to 4 or something, 4 or 5. I don't know exact, but like this is like very slow function. So like you can treat it like as a constant function, like it is nearly constant, right? So that's the two optimizations we can perform on DSU. Okay, now uh, like without going now, there are like several applications that the DSU can do. First I'm going to explain you like cycle detection in undirected graph using DSU. Like in my previous session I have also explained cycle detection using DFS only. Now what you can do here is like we can also detect cycles in a graph using DSUs. How we can do that? Let's see. Let's say we have some nodes in a graph like this. I'll taking a very simple graph like this. Let's consider a very simple graph. Now what we create is we basically create a DSU which like represent the nodes like this. We have a DSU which which does not have any connections. Like it has like six different design sets, 1 2 3 4 5 6. Now what we can do here is like we can loop through the edges. Let's say we go through the edge 1 comma 2 first, and then we merge 1 and 2 like this, and then like we would have after the merging we would have 1 2 3 4 5 and 6. Then we merge 2 and 4, like we merge 2 and 4, and then we merge 3 and 4. So after merging these sets we are at this one. uh, yeah, after merging the sets we are at this state. After like we are just included 1 2 2 4 and 3 3 4. So like these 1 2 3 4 are in has been in the same set now. Now like if you look at this edge of 1 comma 3, uh, now we we want to merge this 1 and 3 also, but we see that 1 and 3 are already in the same set. What does that mean? That they are already connected via some path also. So since 1 and 3 is already connected using some different path, adding an edge from 1 to 3, like adding an edge between 1 and 3 will definitely create a cycle here. So we will just say that there was a cycle. So uh, let me like give you some kind of code snippet. uh, I'll just write the pseudocode of it. So how you detect cycles, we will like create a DSU, and we loop through the edges uh, for edge like this. If u and v is already connected, that is fine. How you say check whether u and v is already connected. We find the root of, if u and v are in the same set, then we can say that there is already a path between u and v, and like this, like then there is a cycle, and then we can like just return, break out of this. Otherwise we will just like union sets u and v. That's how simple it is to detect cycles using DSU. And the find set and union set implementation are like just as was explained earlier. Right. So that's how we detect cycles in using DSU. Now, DSU can also be used to find out connected components. Like you may have some idea regarding this. Let's say again you have some graph. We again create a DSU for each node. No, for not, we again create a DSU where we have like n sets, where n is the number of nodes. So initially we have one in our DSU, two, three. It's like this is three, this is four, this is five, this is six, and this is seven. We like just merge. Will like just merge on edges. Like there is an edge from one and two. We'll merge those. There is an edge from 3 comma 4, we merge 3 comma 4, and then there is an edge from 4 comma 5, we merge 4 comma 5. We will get like 3, 4, and 5. And when there is a merge called between 3 and 5, it does not do anything. So like this, and then we merge 6 and 7. So after merging, after merging, we get this thing in the DSU. So, like DSU can also be used to like figure out the connected components inside a graph, inside an undirected graph. So, how will you do that? Like I also explained that, like after you called like the this, you can like also print the size of each DSUs also, like we explained earlier. uh, we also in the union by size, we also maintain a size parameter, so you can also use this to print out the size of each design sets. I'm not going into the implementation of like this kind of component thing, because like it is like very easy with the most straightforward application of DSUs. And the third is like minimum spanning trees using Kruskal's algorithm. So, what is minimum spanning tree? So, first of all, let me explain you what spanning trees are. That is very important. What is spanning tree? Then we'll go over minimum spanning tree. Like spanning tree is more general version of a minimum spanning tree, as the name suggests. Uh, so let's say we have a graph like this, and let's say it also have some weights. I'm going to give some random weights to this, like this. Now, if you look at this, the spanning tree is nothing but uh, a subgraph of this, which is a tree. Like you, let's say we pick, like in the subgraph, we have to pick all of the nodes, like this node, this node, this node, this node, this node, this node, and this node. But we don't pick all the edges. Uh, like any, let's say we pick some subset of edges such that it becomes a tree, like this. Why it is a tree? Because you may know that a tree is an undirected graph with no cycles. So after removing all the cycles, we get some tree, and this tree is called spanning tree. of this graph, right? So spanning tree is basically a subgraph which includes all the nodes but has no cycles in it and is connected, right? So that is a spanning tree. It is a subgraph connected but has no cycles. Okay. So what is minimum spanning tree? Uh, it is generally referred as MST. What is minimum spanning tree? So minimum spanning tree is that spanning tree in which the sum of weights of the edges picked inside the spanning tree is minimum possible. So let me use this example only. So in here, like if we look at the weights, like 3, 7, 2, 6, 5, 8, 1, there are two spanning trees we have. One, how many spine trees do we have? We have basically like a lot of spine trees, basically a four spine trees. We can remove this edge and still get a spine tree. We can remove this edge and still get a spine tree. We can remove uh, this edge and still get a spine tree, and remove this edge, we still get a spine tree. So there are basically four spine trees for this graph. Now out of those spanning trees, what are the sum of edge weights? One is like if we remove this edge, like there are four options we have. If we remove the edge with the highest weight, then the sum of weights of the edges will decrease by maximum, right? So in this case, like 3 plus 2 5 plus 6 11 16 24 25. So in this case the minimum spanning tree has a total edge weight of 25, and the minimum spanning tree is this only. This is like, this is also a spanning tree, and it is also a minimum spanning tree also, right? uh, I'll give you a 5-minute break. If you Yeah, I'll give you a 5-minute break. I will start again in 6:37. By the way, if you have any questions, you can ask me right now. I'll be happy to answer those. Yeah, the Hari is asking. So we iterate from the highest to lowest weight edges and greatly remove the edges, which on removing don't cause multiple components. Yeah, that's what Kruskal's algorithm does. Yeah, that's how we figure out the minimum spanning tree using Kruskal's algorithm. Is making a graph acyclic a sufficient condition for spanning tree? Yes, the graph needs to be acyclic but also connected. You can't have like if you like disconnect all of the edges, it's not a spanning tree. Like if you remove all the edges, it is still acyclic, but it is not a spanning tree because it is not connected. Will DSU work for directed graphs? Because we cannot union two sets based on size. Uh, like you want to use DSU for directed graphs, but for what? Directed graphs does not have a concept for connected components. They have like strongly connected components, and directed graphs does not also have like minimum spanning tree. Hmm. Like there might be some specific problem which might require DSUs for directed graphs, but I'm not sure what you are asking. Rudra. Can there be more than one minimum spanning tree for a graph? Yes, of course. Um, let's say in the minimum for creating a spanning tree out of an undirected graph, what you can observe that it is sufficient to just remove the edges from cycles so that it does not stay a cycle. So you can cut this edge and still get a spanning tree. You can cut this edge and still get a spanning tree. So let's say that both of these edge bits are like, let's say, 9, 5 and 4. So there are two minimum spanning tree. You can okay, it is 9. You can cut this edge and get one spanning tree. You can cut this edge and get a spanning tree. So there are two minimum spanning tree for this one. Could you please explain cycle detection using DSU? Okay, I have explained it earlier. Like what you do here is you create a DSU. Like let's say in this graph we create like let's say, let's get a very simple graph for now. 1, 2 and 3, and you create a DSU for 3 nodes. And what you do here is like you iterate on all of the edges, like for 1 and 2, and you connect 1 and 2. Then you go over this edge, 2 and 3, and then you connect then you merge this set with this set, and then you get this DSU. Now when you go over this edge, like 1 and 3, so if you look at the DSU, uh, 1 and 3 is already connected. So this means that if you like take this edge, it will definitely create a cycle. So that's how we can use a DSU for detecting cycles. Okay. uh, like now the break is over. Now we will go over Kruskal's algorithm now, and then we will do a problem on DSU. So how Kruskal's algorithm work? So Kruskal's algorithm is like there are two different algorithms for like I know of two algorithms. Like there is also a third one. I don't know. I forgot about it. Like there is two MST algorithm we know. There is one Kruskal. It uses DSU for optimizing it. Like it does not require DSU, and the other is Prem's algorithm. And there was also a third one. I don't remember its name. uh, like it's not important. In most of the questions, like you can just use Kruskal and get away with it. Like in most of the problems, you don't even require to use Prem's algorithm. Uh, Sadly, okay, this is Prim's. Sadly, we will not cover Prim's algorithm in this session. Mm, like because you can get away with minimum spanning tree using Kruskal's algorithm only. I'll send you the links from where you can study Prim's. It's like very intuitive and very simple algorithm for finding like TSU. It uses like priority queue for it uses priority queue for like figuring out the minimum spanning tree. So how Kruskal's work? For first step, let's say we have the same graph again, right? Uh, 7, 6, 5, 3, 2, 3, 1. Right. Uh, how I like to imagine Kruskal is, let's say like this. Imagine like you like removed all the edges. Let's say you remove all the edges. Like I need to redraw the nodes. Right. We removed all the edges and we are just left with nodes. Right. Now what we'll do here is we go from edges from the smallest edge weight to the largest edge weight. So in this case, from one edge weight with one, like two, third, third, fifth, sixth, and seventh. Basically, we iterate edges in the sorted order, and then we keep connecting the nodes in the minimum spanning tree also. So, like if we like look at this edge one, so this is between this node and this node, and this node, these two nodes are not already connected by some any other path, so we will just connect them and add this to our MST, as simple as that. Then we go over this node and the same story, we will like connect them, and then there's three, so we will again connect them. Then there is another node, it is not already connected, so we connect them. Then we have edge weight with 5, these two are not was not already connected, so we connected them. Then we have a node with 6, so we connected. But for this node, this edge, sorry, for this edge, these two nodes are already connected. Like you can see that these two nodes are already connected. So creating drawing an edge will create a cycle, so we do not include this into the MST. So the algorithm is very simple. The step is prepare an edge list of the graph, sort the edge list by weight, and now we imagine that we removed all the edges from the initial graph and just kept the nodes. And now for each edge u comma v, which is in the smallest to largest order according to the weight of the edge. And now there are two conditions that you both, there must exist a path from u to v, or there does not exist a path from u to v. So if nodes u and v are already connected, v does not include this edge because that there was like already a path from u to v, so we can like remove this node. And otherwise, if it is not already connected, we add an edge u comma v to our MST and connect u comma v. That's how crystals work. So where do you use MST? In all of these steps, like 1, 2, 3, 4A, 4B, where do you think we use our TSU? Like I've put an hour effort for the TSU, like where do we use it? So in the 4A step, like how do we check that the nodes u and v are already connected or not? The simplest approach you might think is like we can run DFS from u, and like if at some point we reach node v, then node u and v are already connected. The other way to do it is maintain a DSU, and as we are adding edges, like we can maintain a DSU, and as we are adding edges, we are also merge the sets, uh, merge them in DSU also. So if you keep on merging these, and like at this point, if you want to check whether this node and this node was connected, let's number it, name it. Let's name it A and let's name it B. We want to check whether A and B is connected or not. So if we maintain our DSU properly, then we would find out that A and B belongs to the same set in the DSU, because we have merged everything, merged this, merged this, merged this. So A and B should be in the same set. Okay, so you can figure out whether these two nodes are connected or not in near constant time using DSU. Like it is technically inverse Ackermann function. Okay, so how will you code it? That we will look at a very simple snippet. So yeah, that's the same thing. How will you check nodes U and V is connected? For the step 4a, we will use a DSU. So how will you implement? How will you code it? So basically, we will require an edge list. Uh, so this edge list has a node from U to V. There is an edge from U to V, and there is also a weight in it. So there are three things in this edge list. So we stored the edge in pair of int, comma pair of int comma int, where first is for weight and second is for U and third is for V. And then there is an n. I don't think you require this parameter. We can just ignore it. Then let's say we declared those functions of DSUs earlier in the code. We first of all sort the edges, and since the first pair, the first int is weight, it will sort it by weight, from the smallest edge to the largest edge. And then we store a total weight. Like for minimum spanning tree, the goal is to minimize the sum of weights we used in the spanning tree. So this function returns the minimum, the weight of the minimum spanning tree total. Okay, so we iterate over the edges. There are two things in the edge, like the weight and the edge information itself. The edge information is from where it starts and from where it ends. So what we have, what I have explained, that if uh, the edge is already connected, like the nodes, uh, the endpoint of the edge is already connected, like the find set of edge dot first equals find set of edge dot second. What does it mean? That both of the nodes are already connected. Then we continue, we skip this edge entirely, because there is no need to connect them, and we can save some weight by doing so. Next, if this edge is not already connected, then what we can do is we increment the total weight and union both of the sets and return the total weight. And that's the implementation of the Kruskal's algorithm. Uh, that's the theory part of today's session. I've explained you DSU in much depth. There is more to DSU than this. There is DSU with rollbacks. There are lot of advanced stuff you can find, but this is what I'm going to cover right now. The next thing is I'm going to do a simple problem on DSU. Okay, I will give you a few minutes to read this problem. It is you can search, um, you can read this problem. I'll increase the font and tell me the approach in the chat. I'll give you 5 minutes. Any intuition, proof of optimality of why this greedy strategy works? Uh, like you can find a very formal proof in the book. Which book? Like there is a common book I have read. You can find a very formal proof there. But I don't think it is very. It is not important to understand it. So isn't a height more appropriate criteria for merging than size? Yeah, you can like there are like two types of union. Like there is union by rank also, where they merge by height, and there is like union by size. But like both of them gives you like both of them are pretty much equivalent if you think. Like if the DSU has like in most cases, most practical cases, if the DSU has like higher weight, most often or not, it has like more height. Sir, we will create the TSU in reverse order of queries. This way, we don't need to delete an edge, but instead add edges. Right, right. Omraj has got like Omraj approach seems correct. EFDDCCV is trying to prove uh, the optimality of Kruskal's. Like the intuition is right. I'll give you 2 more minutes for this problem. Let me show you the constraints. Like the n is up to 50,000, m is 100,000. There are like 150,000 queries, and you have like let me show you the example. Just yes. Okay, so I'll explain you the problem. What it says. So you are given an undirected graph and a sequence of operations of two types in the following format. You can cut an edge, that is you remove an edge from u comma v and ask u comma v, like check whether u and v are in the same connected components or not. So like I'll explain this sample. So initially there was an edge, like the this is 1, this is 2, there is an edge from 2 to 3, and then there is an edge from 1 and 3, this is 1, right? And there are like 7 queries to this. First of all, they asked whether 3 and 3 is connected or not. So, 3 and 3 is of course connected, so it is yes. Then they cut this edge. So they removed this edge, and they asked whether 1 and 2 is connected. Yes, they are connected. Then they cut 1 and 3, and then they asked 2 and 1. Now 1 is like disconnected from 2, so it should give no. And the last thing they said, they cut 2 and 3, and they asked whether 3 and 1 is connected. It is also no. So hope the question makes sense now. So there is also a very uh, good constraint that each edge mentioned in the operation of type cut once. Like each edge is mentioned in operations of type cut once. What does it mean? It means that they cut each edge at least once. So at the end of all the queries, we are left with just nodes and no edges. So what does it mean? Like we can like just skip, like we can just skip reading edges also. No, we have to read edges, like, but this does not do anything for us. What we can do is we can go in the reverse, as Omraj said. We go in reverse, like at the end of all of the queries, we are left with no edges. So like let's say we answer the last query first. We can be sure, since every edge has been cut at least once, we can be sure that at the end of all the queries, we have no edges at all. Now, they asked 3 comma 1. So, of course, it will be disconnected. So, we print now. Then they cut 2 comma 3. So, before cutting, for these queries, there would be an edge from 2 comma 3. So, we can just add an edge from 2 comma 3 for these queries. Adding an edge in DSU is very easy, but like deleting in DSU is very tricky. Like most of the cases, you have to like apply offline. Like you have to solve the problem offline most of the times. There is like some weird tricks also. I forgot its technique name. Like in it basically uses a segment tree on DSUs also. Like it is very complicated to remove from DSU. Okay. Then they asked 2 comma 1. For this also, it will be disconnected. Then they told to cut 1 comma 3. What we do the opposite of cutting. We draw an edge from 2. Okay, 1 comma 3. We draw an edge from 1 comma 3, because there must have been edge from 1 comma 3 for these queries. And when we are drawing, we are also merging them in DSUs. Okay. Then they asked 1 comma 2. Now 1 comma 2 is connected. Then they said cut 1 comma 2. So we do the opposite and like add an edge from 2 comma 1, and in DSU we merge 2 and 1, right? And then like ask 3 comma 3, it is like connected. So the answer is yes. I will not code it right now. I'll like I've coded it just before the session. I'll show you the implementation, my implementation basically. This one, maybe showing here would be easier. Yeah, this one. Right. So how it is implemented. First, we have like the headers. Then I created a global constant n, which is set to 25. That I don't need to set it this high. We can like just set it to like 1e for 50,000 or something, because there was the maximum number of nodes can be 50,000, but for the safe side, I just set it 25. It does not matter really. Then we have like a parent array and a size array. Like we are using both union by size and path compression both. So in the find set implementation, as I've explained, if v is like I've just explained like the implementation. Like this is the find set implementation, and in the merge operation, like I interchangeably exchange the term merge, union sets, so it doesn't matter really. So we find out the root of u, find out the root of v. If they are already connected, we return. Make the make the v the smaller one. In this case, we make the v smaller set and u the larger set, and like then we actually create an edge from v to u by setting the parent of v to u, and then the set u has all the elements of set v, so the size of u need to be incremented by size of v, right? Now in the main function, first of all, what should be the initial values of this parent and size? I have not explained it earlier. So uh, initially, like we have like from 0 to capital N minus 1. uh, these are the indices for this, and like initially we, I like to assume that they are all disconnected disjoint sets, like all of the sets of size 1, right? So like I initialize it like this, like the parent of I is equals to I, like all of the nodes are root node, and size of I is equals to 1, because that those sets are all of size 1. And then I started reading the input. N is the number of nodes and M is the number of edges, Q is the number of queries we are given. Okay, now as I said earlier, that we can like just ignore after like reading the edges, right? the This doesn't matter much. We are just using DSU and that's all. We are not even constructing an adjacency list or matrix, anything like that, right? Now we want to solve these queries offline. That is, we, what does offline mean? There are two ways to like solve queries. Like one is online, like as you read queries you give the output immediately. But the other method is like offline, in which like you read all the queries first and output, like then give answer to the queries in an order which is convenient for you. So in this problem, it is convenient for us to go from bottom last query to top query, since, right? So like we stored the queries in like this pair of string, pair of int, where this string represent the operation. There are two types of operation: ask and cut, and these pair represent the edge, right? So we read the operation, the edge, and store it in our queries. Now we reverse the queries because we want to process these queries in reverse order, and then we also store the answer in a vector, because like we, the, like the order we have to reverse the answer also, right? The question demands that we answer in the order we have, they have given queries in the same order. So we have to like maintain a vector of answer and then reverse it afterward. Now how do we do it? So first of all, we read all the query, like we iterate over all the queries in the reverse order, like remember we have reversed it earlier. And then like we go to like this syntax is called like, I don't know what this syntax is, but this is called operation, and this is UV, that is the edge. And now we extract the edge endpoints U and V. Now, if the operation is cut, what we do is we do the exact opposite of that. Instead of cutting, we merge them, because, as I explained, we are doing queries in opposite order. Otherwise, we like if the operation is asked, we check if U and V is already connected. If it is already connected, the we push answer yes. Otherwise, we push in answer no. And now we like reverse the our answer vector and just print it out. Yeah. That's the solution of this problem. Mm, let me chat. If you have any question, you can ask. attendance. The attendance link will be shared. Is CSCS counting room problem? Got TLE. Counting room problem. Okay, this problem. Uh, like in this problem, I tell you like check if like there is not no infinite loop or something. Like you must be like implementing using DFS and doing it wrong somehow. Sir, can the DSU be used for more general problems? Uh, DFS, BFS can be modified to suit the problems at hand, or is DSU very problem specific? Like DSU is not like more very widely used data structure. In graphs, it is used a little bit, but it is not like very widely used. Like there are some hard problems that can be solved using DSU also, and like don't like you can model your problem to graph and then apply DSU something like that. Okay, bye bye. The session is over. It did someone solve it?